Hi everybody, thank you for taking part here today for our online Space Week seminar, especially our invited speakers, but also to all the students and educators. There's a lot here. It's very nice to see such a strong interest in exploring our understanding of the universe. This is our third CosmoVerse seminar, exploring our shared cosmic history with students and educators from across Europe and neighboring areas. CosmoVerse, as you may have seen, is a network of over 600 researchers in Europe and over 800 globally, with the aim of unifying efforts and confronting the most pressing questions in our understanding of the cosmos. So the main aim of CosmoVerse is to establish a synergy between theoretical data analysis and observational physicists working on frontier challenges to understanding how our universe is expanding, evolving, and the source of these processes. To know, you can also follow us on Facebook and Twitter or X, as well as on our website. Moving to our first speaker, Professor Emmanuel Saridakis' research focuses on fundamental questions of our universe, with topics spanning theories of gravity, dark energy, observational data analysis, black holes, gravitational waves, the early universe, and lots of other things. He has held positions across 3 continents, including the USA, France, China, Chile, where he is right now, and currently serves as a research director at the National Observatory of Athens. He has been recognized with multiple awards, and according to the famous Stanford University list of the most influential scientists worldwide, he's in the top 0.04% of world scientists within all fields. His research has been instrumental in addressing cosmological tensions, exploring new physics beyond our standard model understanding of the universe. He participates in the U.S.A. key LISA science mission and NASA's Psyche mission, and is a representative of Greece in many cost actions. Emmanuel, please start in your own time. Thank you.
Thank you very much, Jackson, for this nice introduction and also for the great opportunity to give this talk. And thank you all for being here, all the participants all around Europe. So we are going to talk on the Big Bang Theory, and I will try to convince you in the next 20 minutes why the 21st century is the century of astrophysics and cosmology, and we are living in very, very interesting times. So first, let me remind you that the whole history of science is a history of tensions between our theoretical predictions and the new data. So we build theories, describe the universe, and these theories work in a very good way, very successfully. However, as technology advances, we have the ability to make more accurate data, more precise data, and this data puts our theories into questions. Okay, and then we need to change our theories in order to be able to describe the universe in a better way. Now, astrophysics and cosmology, the last 20 years, have become precision sciences. Why? Because we have the technological ability to do observations that we could never think of in the past. So the question is, are we approaching also a scientific revolution? Let me sketch you very briefly how the history changed. So the first, let's say, gravitational and astronomical model was the Aristotelian Ptolemaic cosmological model, right? The Earth is in the center of the universe, all the planets orbit around it, and for instance, gravity, heavier bodies fall faster, etc., etc. This was the most successful and long-lived cosmological paradigm until new observations, more detailed observations in the Middle Ages, mainly from the Persian and Islamic school, but also in India and China, put the details of this model into questions. And then we have the 1600 revolution with the observations of Brahe and Kepler that spent 30 years of their lives observing the motions of the planets, and the Galileo's first experiments on gravity, right? So all this put the Aristotelian Ptolemaic model into strong question, and of course, then we're coming to Newton, which built the first concrete theory of gravity, right? And it's the first time that we understood that it's the same force that makes apples falling on Earth and the planets rotating around the sun, the force of gravity. And for the first time, we understood that in order to understand the laws of the stars and do astronomy, you need to have a theory of gravity, because gravity is the director of the evolution of the solar system and of the universe. Newtonian gravity was a perfect, successful theory in agreement with all data until the advance of technology in the late 19th century put Newtonian gravity into question with the anomalies in the Mercury's motion. So we had to go to a new paradigm shift to the theory of relativity built by Einstein, but also other people like Minkowski, Hilbert, and Schwarzschild. So this is the questions of general relativity. Don't pay much attention into that. And relativity made a revolution in the way that we understand gravity. First of all, we have the equivalence between energy and mass, but the revolution was gravity is not a force anymore. It has been embedded into the geometry of space-time, right? So if you have a heavy object, as the sun, it curves the space-time around it, so the Earth falls into this curved well, space-time, and this is how we feel gravity. So space-time tells matter, matter tells space-time how to curve, and the curved space-time tells matter how to move. I want to sketch here that the theory of relativity is not just a theory, right? It has been verified millions of times. We are using it every day when we are using the GPS or our precise clocks. If we have two precise clocks and I leave one here and I put one in an airplane and it goes to London and back, it will show different time. The difference is 1/billionth of a second, but we can measure that. Why? Because time flows slower if you move faster. In the same way, in this room, if I have an atomic precise clock, I can measure that the time in my head runs slower compared to the time in my feet, because my feet are closer to the Earth's center, so gravity is more important, so the curvature of space-time is increased. We can measure all these things. So this is a take-home message. Relativity exists. Now, what I want you to realize is that the solution of the problems, of the observational problems, so the discovery of general relativity was not an immediate procedure. It took 60 years. So for 60 years, people were trying to bridge the gap between Newtonian gravity predictions and the new observational data. So 2 generations of physicists needed to solve the tensions, right? So the solution of these observational problems is not an immediate procedure. Now, let me come back to observations. Of course, we are living in a solar system. Our sun is just one star within a cluster of stars within our galaxy, right? So cosmology starts beyond that level. And let me remind you that our galaxy has a diameter of 100,000 light years. Now, if you zoom out, so the camera zooms out, and we go to 1 million light years, we have the group of galaxies. So small groups of 10 or 50 galaxies. Then if you zoom out more and you go to 10 to the 7 light years, so 10 million light years, we have the clusters of galaxies. So gravitationally concrete groups of galaxies. A cluster of galaxies may have thousands of galaxies, and it behaves like one object. If I zoom out more, and I'm going to 100 million light years, I have the superclusters of galaxies. So clusters of galaxies. And if I zoom out more, and I go above 1 billion light years, then the universe looks the same everywhere. Mathematically, we say that this is homogeneous and isotropic. You see, this is a map of the universe. You can clearly see every light here is thousands and millions of galaxies. You can see that this region is the same with this region. This is called the cosmological principle, right? So this is how galaxy clusters look. You see, all these are galaxies, and we have a concrete group of galaxies. And this is how the superclusters of galaxies look. So now we have superclusters, clusters of galaxies, right? And that is how we built, this is the most recent map of the observable universe. We know that there are more than 1 trillion galaxies. Most of them have tens of billions of stars, most of them having planets. You can clearly see now the cosmological principle, right? This region of the universe is the same with this region of the universe, right? So we are living in a random star, in a random region of a random galaxy, within a random cluster, within a random supercluster, in a random region of the universe. So next time that someone will behave to you like he's being the center of the universe, you will just tell him that the universe does not have a center. So it's not like that. Actually, it becomes more interesting 90 years ago, where this guy here, the best basketball player of the University of Chicago, Hubble, he became a famous astronomer, he observed the following thing. He observed that the distant galaxies move away from us. And actually, the further they are from us, the faster they move away from us, right? And this is the famous Hubble law. So the speed that the galaxies move away from us is proportional to their distance. And this coefficient here is the Hubble function, the Hubble parameter, the quantity that determines how fast the universe, the galaxies move away from us. Now, you could say that, okay, if all galaxies move away from us, then we are the center of the universe. No, it's not like that. It's not that the other galaxies move away from the Earth. It's that all galaxies move away from all galaxies. As we say scientifically, the universe expands. Actually, it's the space-time itself that expands. You see, take an olive bread that you put it in the oven and it expands. This olive here sees all the other olives move away from it. But this is true for all olives. So the whole bread expands. In the similar terms, it's the whole universe that expands. Okay, but then you should think, if the universe expands, then what will happen if I go backwards in time? If I go backwards in time, all galaxies will be closer and closer and closer. And if you put down the number, you can find that around 14 billion years ago, all the galaxies that I was talking about, everything that we see in the universe, was concentrated in a super dense and super hot point, right? And this point went through a big bang. And after that, the universe expands and cools, expands and cools. You see how we deduce that? Okay, so this is a rational theoretical consideration. And this is the theory of the Big Bang. So 14 billion years ago, all we see that in the observable universe was in a super dense and super hot atom, and we had this explosion, and actually the universe expands and cools. By the way, the name Big Bang was given to the theory by an opponent of the theory, by Hoyle. Hoyle didn't believe in that, and he said, this is nonsense. This would ask for a Big Bang. So he named the theory he was opposed. And you can clearly see now how we can calculate very easily the age of the observable universe from the Hubble's law. Of course, so the age is just proportional to this Hubble function, right? So the universe is not static, it has a history. This is very important. It's a dynamical thing. Okay, but how can we prove that? Remember, in science, we always have to prove things. So the Big Bang has a very important prediction, because in the very early stages of the universe, the first seconds after the Big Bang, the temperature was huge, trillions of Kelvin degrees. We had a soup of nuclear reactions, right? You had neutrons connecting with protons, building helium nuclei. Now, in this nuclear procedure, we have the production of photons, a lot of photons, high energy photons. So if the Big Bang has happened, we should have photons everywhere. However, the universe, of course, expands and cools. So these high energy photons today will have been stressed due to the universe expansion, and today their wavelength will correspond to microwaves. So if the Big Bang has happened, the prediction is that if you look at the sky in every direction, you should receive photons at the microwaves like we have in the microwave ovens. Indeed, in 1967, these two guys, Penzias and Wilson, accidentally, they were trying to measure something else with their antenna, but they found that from every direction in the sky, we get microwaves. What are these microwaves? It's the echo of the Big Bang, and it is the proof that the Big Bang happened. And actually, they got the Nobel Prize, although they discovered that accidentally. And the last thing I'm going to tell you is the following. Back in the 1499, Amerigo Vespucci was the first guy that went to explore the delta of the Amazon River in Latin America. He just explored 40, 50 kilometers of that. But he realized that in order for this big structure, this big delta, to have been built, then it means that the land here needs to be thousands of kilometers long. So we have to do with a huge continent instead of a small island. Remember, he didn't see this whole continent. He just observed 50 kilometers of the delta of the river, but he realized that in order for this structure to have been created, then we have to do with a huge continent. And of course, this continent got its name from America. The same things happen in the universe. Because the universe has the structure that we see, not only we deduce that this observable universe is not the whole universe, but it's just a tiny part from the whole universe, which may be finite or infinite. And this is the theory of cosmic inflation. So you see, after the Big Bang, our observable universe comes from a tiny region of the whole universe. And actually, our universe is a bubble within a sea of many other bubbles. Why? Because if our observable universe was the whole universe, it will look like that. Because it has these properties, we deduced that it's just a tiny part of the whole universe. So, coming to the end, I hope I convince you that the 21st century belongs to astrophysics and cosmology, and we have a huge amount of technological capabilities. We have more than 100 space telescopes on Earth. We build really huge telescopes of 20 or 30 meters diameters. We have opened the new window of observing the universe through gravitational waves. So if you put all this together, we have a new huge amount of data that put our theories into questions, as we will hear in the next talk by Danny. So that's why we're saying that we have a new crisis of cosmology. You see, our theories, general relativity for gravity, and our cosmological scenarios work in a very good way. They are very successfully. However, now we have a huge amount of new data that put our theories into questions. And there is a discussion in our community whether new physics is around the corner and whether we should proceed to a paradigm shift and change something or modify something. And actually, the CosmoVerse action that we are all participating has as a focus exactly to investigate these new tensions between theories and data and see what's going on, see how we are going to proceed. So I will stop here. Thank you very much.